physics is about capturing regularities in nature that are universal and can apply regardless of the substrate, regardless of the scale and the place where these things happen to be.
Are you interested in how quantum physics is influencing the future of cities? What do you think about the connection between knowledge and urban evolution? How can we create better urban environments for knowledge creation? Stay tuned for answers from Chiara Marletto.
What is the future for cities? Do you want to learn more about them? Do you want to know how others think about them? Do you want to be part of the conversation? Then this is the right place.
Welcome to What is the Future for Cities podcast. Today, we will interview Chiara Marletto, scientific researcher at the University of Oxford. My interviewing partner is Ben Wash, and we will talk about Chiara's vision for the future of cities, the effects of scientific evolution, the best environment for knowledge creation, and many more, as a special edition part of the Podcaston 2025. So let's start with a proper introduction. Chiara Marletto is a research fellow at Wolfson College and the physics department at the University of Oxford. She holds degrees from Oxford and the University of Turin. Her research focuses on the foundations of physics, spanning quantum information theory, condensed matter physics, quantum biology, and thermodynamics. Chiara has pioneered a novel approach to physics, constructor theory, and has applied it to fundamental questions of control, causation, and the nature of information in physics. Her work has also explored how essential features of living systems, such as self-reproduction and evolution, align with fundamental physical laws. Recently, she has discovered a new method to test quantum effects in gravity, based on constructor-theoretic ideas. She is the author of The Science of Can and Can't, her first trade book. This is also a special episode to be part of Podcaston 2025, a globally coordinated effort for podcasts to highlight a charity of their choice. WTF for Cities is happy to participate in this third edition of the Podcaston with thousands of podcasts worldwide. The charity where you can support Chiara and her research is through Wolfson College at the University of Oxford with New Frontiers reference. And with that, Chiara, welcome to the podcast.
Thank you so much for your time. We highly appreciate that you are appearing on the podcast. And let's jump right into this very interesting question from your perspective. What does the future of cities mean to you? Thanks for inviting me to this very interesting podcast. I think it prompted me to think about something that is quite, in a sense, far from my everyday thinking because I'm a theoretical physicist. I think about very abstract entities most of the times. But I think there is a very interesting connection between physics and the future of cities because physics is really like this powerhouse that produces ideas and that changes the worldview that we have. And I think this has happened during the whole history of physics. And somehow this way in which you find a new theory, there's a discovery that changes the way you look at the world, has a deep impact on how we live because it produces new technologies in the long run. And I think that way, the way in which we organize our cities changes dramatically. Can take of an obvious example, which is like you start with thermodynamics that was developed in parallel to the Industrial Revolution. And then you have these engines that get produced. And then suddenly you've got cars. Then you've got to change the roads and invent new regulations to make sure that cars are not crashing into people. And then you try to change the way in which viability goes in what used to be towns with only horses and other kinds of vehicles were moving about. Then you've got trains, then you have stations, etc. So I think for me, the future of cities, when I think of that, really means how are we going to integrate potential future discoveries in the urban structure? You can think of viability, as I was saying, the way in which you structure roads. And also, if you change the mode of transportation, mostly we're using land now, but it could be that at some point we decide to use flying objects instead of cars that use the roads. And then you will have not just planes, but literally to move from A to B within your neighborhood. You might be able to use some flying cars. And then you will have to have different kinds of rules for viability as well. And then there are, of course, these ways in which people cluster around. That's another interesting aspect of cities that I find really intriguing, because I have an interest in information theory, specifically quantum information theory. And in this kind of subject, we think a lot about communication and ways in which understanding physics better can change the way in which we manipulate information. Of course, this has already changed a lot. The internet has already changed a lot the way in which we can get together. You can have remote meetings and ways in which you can meet your colleagues or friends without actually being there in person. Imagining a future in which we integrate AI and universal quantum computers, which we don't have yet, but we will have at some point in our cities, I'm thinking that we may have a really enhanced virtual reality rendering that can help creating even virtual spaces where people can meet without actually being there physically. And I wonder what that might mean for cities. Would that mean that people will be much more spread out in space and then they will be able to connect in this way? And then this may impact also the structure, the way in which we arrange housing and so on. So that's like another big direction along which I think I'm thinking about the future of cities. And then the third one, maybe this very futuristic path that goes together with thinking of how new kinds of programmable machines could be integrated in the materials that we use. We're now using computers really very much into our daily lives. They become basically our helpers. But there are other kinds of objects that you can think of programming. We can talk about them in broad terms as constructors. So these are machines that you can program to perform different tasks. So that you can think of them as programmable 3D printers, which, of course, we only think of them in theory now. We have some instances, but we don't have a way of producing them in a way that just like what we do with computers. But imagine like in the future, if we had this technology available, you could imagine integrating them into some materials. And then you would have some interesting ways of repairing things around in the city. So you might have nanorobots that are incorporated with a traffic light. And then when a traffic light dies, instead of calling someone to fix it, you can just rely on these guys that you program to come out and fix the traffic light itself. And more generally, you can even think of more sophisticated ways that we can program even like at the level of molecular structure. Maybe you can have materials that are more resilient in the sense that they can self-generate themselves and regenerate and fix themselves when they get eroded. There are lots of sci-fi tales about things like that. They don't exist yet, but I think physics has the power of thinking of these things. That would be very interesting to understand how you would integrate something like this in a city landscape.
I love your researcher brain immediately launching on what kind of questions can we ask about the future of cities. This is really awesome. Before we jump into quantum physics, because that would need some time to and also to explain, you just mentioned resilience and regeneration on the molecular level. And in the city sense, resilience can mean a lot of things. So what does resilience mean to you, and how is resilience and regeneration connected for you?
This is a really nice question. I like that you picked up on that point because it's very close to my current thinking, my own research. So if you look around, you can see that there are objects in general. This is in physical reality at large. I think you can see that there are objects that wear out and get progressively eroded and destroyed with time. And others that have this property that they do something and then they somehow get reset to their own initial state approximately. So this is very common, obviously, in the biosphere. So if you think of living systems, simple bacteria, even just one cell, they have some amazing self-repairing abilities. Even when there's a replication of the DNA, there are these enzymes that can check that the replication has happened faithfully. And this ensures that for quite a long stretch of time, these entities can maintain their shape, so they are resilient. So this ability to maintain one's own appearance or functionality, despite the environment or the noise trying to get in, is a thing that is typical of the biosphere, as I said. So it exists at all levels in the living world. And also in other inanimate matter type things, such as crystals and other kind of condensed matter structures. And so I think resilience and regeneration are closely related because the laws of physics are set up in a way that they're not really helpful or they're not trying to fix errors as they come up. If you happen to be a complex structure of some kind, you will have to fight very hard to maintain your shape. Otherwise, the natural things that are occurring in the universe are things that are made of elementary components or they follow simple symmetries like what happens at planetary level and so on.
But I think already like an aggregate of many molecules put together, that is a thing that appears to be relatively unusual compared to the stuff that's naturally occurring according to the laws of physics. And so for that to maintain itself, there has to be some mechanism that ensures regeneration. And I think that's how you get really from these simple crystals to replicators to life. The mechanisms for regeneration, which become more and more complex as the molecule gets more complex, of course, they are very complex in a human body, are vital for the resilience of the entity in question. So this is the connection. And this is simply because the laws of physics are the way they are. Because, of course, if we had laws of physics that were particularly designed to help us survive or be regularly upgraded or updated or error corrected, then we would not need any internal mechanism to correct errors. But that's not the case. The laws of physics are not designed for us. And I think life has had to come up through natural selection and other things with mechanisms to make themselves resistant. And cities are an instance of this. Because cities are like this kind of broad idea from biology of the extended phenotype. They're part of the infrastructure that we humans came up with throughout our evolutionary history in order to survive. So I think from very primitive cities, which were just aggregations of humans in sort of tribes and things, and then going through ancient times with more sophisticated structures like in Greece and Rome, etc., and then throughout the Middle Ages and then the Renaissance, etc., and then the European towns and so on. And then how that's also, there were powerhouses for some ideas that were created during history. So those places were really important to preserve humans, and then the ability to self-preserve that humans have was embodied in the cities themselves. It's interesting to see cities as a constructor, if you like. So this entity that can do a transformation and stay, let's say, approximately unchanged in its ability to cause it again. And somehow it's up to us to find ways of doing this more efficiently. And I guess part of our mental problems and so on are us trying to figure out ways of being smarter in making waste go to zero within the limit of the laws of physics. And of course, physics has a lot to say about this, because ultimately how much waste there has to be in a certain transformation and what is the minimal amount of waste, whether you can reduce it to zero or not, depends on the laws of physics. Thermodynamics is one example, but there are more general laws that you can think of that have information theory in them and so on. And from my point of view, from the point of view of a fundamental theoretical physicist, I find very interesting this question of how can we make a city work in a cycle as much as possible so that you have zero waste? So can you make it really so that it can self-heal, it can regenerate itself when there are some errors or little things that start going wrong, but without needing a huge overhead in terms of extra material that you have to put in and then waste that you have to generate as a result of the error correction. And this is really a similar question to what you're asking about the workspace in a computer, when the memory and so on, and how much memory you need in order to error correct. They are very similar questions. It's just the substrates are different, but you can see them as very similar issues, which is why I'm interested in them. And of course, okay, to some degree, I guess we should be interested from purely survival, from the point of view of seeking ways to be sure that we are surviving. But I don't think that's what I'm thinking, really. I'm just interested because I like the ideas. Ultimately, they're useful.
You also answered my follow-up question, which I haven't asked. What does the city mean to you? Because you mentioned that it's part of a constructor.
And I have a question about that, because basically I read The Beginning of Infinity, Fabric of Reality, and your book, The Science of Kant, when you connected information theory with physics. I also read Fanny's PhD about smart cities. I did my homework for this conversation, and I would like to get some insight on how do you pick the right abstraction level to look at a situation, to look at a problem, to find a way to error correct. Because we can look at like the subatomic particles from like quantum physics, atoms, molecules, DNA, biology, then big jump, humans, then cities. Fanny said multiple times that in her opinion, the city is the interaction of agents inside the humans inside. It's an emergent property of the interactions of a human. If you cut a city in half, then you have two cities.
It's a good point.
And I'm fascinated by this idea of you have multiple layers of abstraction, you have emergence. And I'm curious, how do you think about this? And can you connect it back to construction theory?
This idea of multiple levels of abstraction is really important. I think physicists usually, traditionally at least, think that there is only one level that matters, which is the level at which the elementary components exist. We're talking about the electron, protons, and then below that. Some physicists even would like to think that chemistry doesn't make much of a difference, in the sense that when you go above the atomic scale, you already get to something that's not fundamental. That's one point of view. I would say that's like an extreme reductionist point of view. And then you get different kinds of approaches in between. And I guess maybe I am in one of those in-between approaches, in the sense that, yes, I think that this underlying level is really important, in the sense that it really sets some limitations to what can happen as you go above in size, in a way. Higher level aggregates, what can they do? Biological systems, humans, cities, and other things. However, I think that there are laws that even are part of physics, but they do not necessarily apply only to that level. So in higher level, if you go at higher level of abstraction, for example, you look at computers, which is what, the example I was giving earlier. Computers are not elementary particles by any stretch of imagination. They're just not. They're just macroscopic entities, and they're even produced by humans, as far as we know. However, they do have regularities, right? So they obey certain laws. And these laws are exact. So there are laws of information which do not apply just at the level of macroscopic level of computers. But I think if you manage to create a computer out of very microscopic components, the laws will be still the same. And so with the case, if you use different materials somewhere else in a different context, and maybe there are some alien civilizations that are doing that right now, they will still obey the same laws. So that is an example of a law that applies at different scales and not just at a microscopic scale, which is a regularity in nature that matters for physics, because physics studies these things. Physics is about capturing regularities in nature that are universal and can apply regardless of the substrate, regardless of the scale and the place where these things happen to be. So in a way, I'm very happy to think that there are laws that one can see emerge at different levels. And to appreciate the whole reality, you need to really take all of these laws into account. And some of them are not reducible to the lower level of microscopic particles. It doesn't mean that they are in contradiction. I'm not suggesting that the higher level laws are incompatible with the lower level laws. Everything is somehow coherent. However, if you wanted to reduce all of these higher level laws to the microscopic dynamics, you would just miss out on lots of things. That's somehow my point of view. And constructor theory is one example, like in information theory, where you're looking for general laws that do apply regardless of scale to all of the things that you can call constructors, so to all of these programmable machines that you can construct at any level. So at the microscopic level, you can make them at the mesoscopic, macroscopic, doesn't matter, but they all obey these general constraints of what they can or cannot do. The same way that I would say energy conservation constrains heat engines. And this is true if you have a microscopic heat engine, which we don't have yet. But I think people are thinking about it. Or whether you have a standard heat engine of the kind that was powering, but still powering the trains and cars and so on. So I think all of these engines are really, doesn't matter what the size is, they're all constrained by conservation of energy. The fact that if you destroy energy somewhere, you need to supply it from somewhere else because the energy is overall conserved. That's a law that is inescapable in a way. A kind of constraint that has a constructor-theoretic flavor to it. And constructor theory somehow takes this logic and makes it more general. And it might apply to machines that we will construct in the future and may actually be of the kind that I was saying earlier, these nanorobots that can construct things and fix things. They could be even part of existing infrastructures if you want to go back to cities. And the important thing is that these things are not, we usually think of them as just disconnected from physics, but I think it's a mistake. They are really constrained by the laws of physics. So what we can do ultimately with the machine, be it small or large, is really down to what the laws of physics are. And indeed, when universal quantum computers were discovered, David Deutsch was one of the people who pioneered this together with others. I think these people realized that if you change the laws of physics with which you compute, so you go from classical physics to quantum theory, which these are two different theories, you get different kinds of computations available, different kinds of algorithms. And so that's an example where the kind of physics really constrains the type of transformations you can perform. And these laws that say how this happens, they stretch across the different levels of explanation that you were mentioning earlier. And so to see and understand them, you really have to take into account the whole picture. I think in my book, I have this example like a cake, right? The different layers. And if you've got a cake with layers, you can't just eat one of the layers. You will miss out on a lot of flavor. You've got to eat the whole slice to get the meaning of the whole cake.
My limited understanding of physics, so bear with me for a second. But on a quantum level, a lot of things are reversible. But if we go up on an abstraction level ladder to a macro scale, things become non-reversible.
Before we jump into that question, Chiara, please explain what you would like people to know about quantum theory and quantum physics, because I'm here to represent the noobs. So let's establish some baseline and then we can go into the details.
From a very general point of view, so quantum theory was proposed about a century ago together with general relativity. So these are the two theories that we're using right now to describe the universe. They both had the aspiration to be universal, so they should apply to everything. It's important to know that they replaced what we had before, which was Newton's laws of mechanics. So the classical physics, we mean Newton's laws, which are still useful to plan things and apply to a certain domain, the macroscopic domain. So if you have to plan out how a car is going to move in a certain way, given a certain initial condition, you can still use Newton's laws. But I think if you really want to know how things work at the microscopic level, those laws don't work. They don't even work to describe how the atoms bind together. So if you use Newton's laws plus the classical theory of electromagnetism, you would see that the atoms can't clump together in the way they actually do. So somehow that was one of the cornerstones when people realized that we had to change the laws to understand better the microscopic structure of matter. That was one of the reasons why, and then other reasons came in. Since we discovered these two theories, I think somehow there has been a huge emphasis on quantum theory being really hard to understand, even though I think general relativity is equally difficult to grasp, but somehow quantum theory has gained this horrible reputation of being completely nonsensical. And I have to say that my colleagues, physicists, are a bit at fault for this, in the sense that they probably like to emphasize how fuzzy and difficult to understand this thing is. And so as a result of that, I guess in the general public, quantum physics is equated with mystery and incomprehensible stuff, that the universe is fuzzy and we can't understand it. I disagree with that. I think quantum theory is really very tight. It makes a lot of sense. It does say things that are a bit counterintuitive and they're mind-blowing. However, I want to say that even Newton's laws are like that. If you think of certain effects that they cause, you've got centrifugal forces and things like that, they are super counterintuitive. When you try to solve these problems, your intuition says, no, but there shouldn't be a force there, and instead there is. So I think physics is counterintuitive, and quantum theory is just doing its job at telling us that the world is not the way we expect it to be, just by judging from our senses. The two things that are important for the rest of the conversation, also in regard to what Ben was saying, I think are that one thing that is particularly difficult to understand about it is that it has a different information theoretic structure from the classical physics that we knew about, and also from relativity, so the theory that describes gravity. That's Einstein's relativity. Einstein's relativity and Newton's laws are both classical from the point of view of information theory. So if you wanted to make a model of them using computational entities, you would be okay with using just bits. The classical bits can be either 0 or 1, and they don't have other states in between, on or off. That's a classical bit, a bit that either can have one or two definite states of existence. Either it's 0 or it's 1, or it's on or off, and so on. Quantum theory allows for more things. That's the beauty of it. So there are these entities that we call qubits, which are quantum bits, it's short for quantum bits, which are the fundamental information entity for a quantum computer. They obey the laws of quantum physics, not classical physics, and they behave in ways that are, in a sense, they contain a classical bit, so they do behave like a bit. They can be used as bits. However, they don't just have these two states, 0 and 1, they also have states in between, where they can be in what in jargon we call a quantum superposition of 0 and 1. Now, what is a quantum superposition? That's the whole problem in explaining what quantum theory is about. So one would have to open a huge digression and discuss that. For the purpose of a simple discussion, it's okay to think of that as being something that is in between 0 and 1. It's a mixture of these two values. But it's not a probabilistic mixture, so it has a lot more into it, and it allows for an awful lot of other phenomena, which are the reason why quantum computers work better than classical computers with probabilities in them. It's not just a stochastic probabilistic mixture of 0 and 1, a qubit. It's really that these states in between are different states of matter, and they have extra properties. And this is the whole quantum issue. But the thing that one has to bear in mind at the very basic level is that simply the information theory structure is different from the structure of a bit. It's richer, and it has a lot more possibilities in it. And this is because there are these quantum superpositions in between 0 and 1. That's one aspect. The second aspect that will be useful maybe for other considerations we'll make later is that because of this tension, because of the fact that quantum theory has this quantum structure that has this information theory properties that are different from the classical properties of a bit, and because relativity instead, which is the other theory that supposedly is universal and should apply to everything, describes gravity, is actually classical, there is a clash between these two worldviews. And so we are stuck with two theories that really work well in their domains so far where they've been tested, but they disagree at the fundamental level in the way they describe how information theory should work. And so when you try to put them together, you get a problem. And so this is the current problem with which we're grappling at the fundamental level. It's one of many, but I think somehow this is one of the most important ones. And it's been like this for a century or more, so it's getting quite boring. So we've made some progress at the theory level to put them together, but these new theories cannot be tested yet because we're not able to, at least until recently, it was thought that experiments that can test these new theories that put together quantum theory and relativity are really hard to implement in a laboratory. So we don't have experiments that can tell us where one of these two theories could go wrong. And at the same time, we keep confirming them really well in their own domain, but we know they don't agree. So it's quite frustrating. And I think that's the state where we are in. So these are the two things you need to know about quantum theory. These are the two most important things, I would say. And then again, in addition to what I said earlier, this is an extra thing, if you like, which is that quantum theory has this, because of this different information theoretic structure, recently in the 80s, people like Feynman, Benioff, Bennett, Deutsch, etc., they thought that it could be maybe possible to use this different way of treating information as a power, a new kind of power for computation. And I think they came up with a new idea for universal quantum computers, which were modeled on the Turing classical computer idea, but they incorporated these quantum effects in them. Surprisingly, for many, turned out that these computers can actually do many more algorithms compared to the classical computers. And I think this gave rise to the whole business of quantum technologies, quantum cryptography, quantum computers overall. And I think now it's become almost like an engineering problem because it was a very theoretical idea in the 80s. And as usual, most people thought that this was a curiosity, wouldn't do anything and so on. And then in the end, actually, it powered very interesting technological discoveries that also brought us to a much better level of technology to manipulate quantum objects. Interesting also from the sensing point of view, from other more applied points of view that I think I find interesting to some degree, even though that's not my focus.
It's quite well known that you and your team working on resolving this. And we can go into the details, but I think you explained that in other podcasts a few times. So I would like to not totally hijack Fanny's podcast and go down the rabbit hole of what happens if your quantum gravity experiment happens. Like, there is two big potential outcomes. And this is when I would like you to go a bit far and try to imagine, okay, based on the two potential outcomes, what kind of technologies may come which affect how we live?
Yeah, I think this is a great question because it really goes right into the middle of this problem that I mentioned just now. One of the blocks that we have been encountering so far in making progress to merge these two theories is that so far it looked really hard to perform an experiment to put them together, to test anything that tries to merge them into what, broadly speaking, is called quantum gravity. Quantum gravity is just a thing that puts together quantum theory and relativity, trying to merge them mathematically in a way that is consistent. That is already a huge issue theoretically. So I think these proposals are the result of the work of lots of people who've been thinking hard and trying to find beautiful, amazing ways of putting these things together. But unfortunately, it looked like it was very difficult to test any of the predictions of these theories, which is why things like loop quantum gravity, string theory, you've heard of these names sometimes in the press. They are mathematically sound, they work, but they make predictions that are really hard to test usually. Recently, we have also using ideas from constructor theory, we've found this way of testing one aspect of gravity, which is quantum. This is only one of the many properties. So if you like, it's a simple experiment. It only tells us whether gravity has some non-classical features, some features that are not of the bit kind, but of the qubit kind. And it's based on information theory ideas, and which is why I think we managed to get this experiment doable, not on very high energy scales, but on low energy scales that can be realized in a laboratory. And the idea is really to create a kind of correlation between two mass that can interact with gravity through gravity only. And if gravity can create this kind of correlation, which in jargon is called entanglement, it's a strictly quantum correlation, then gravity is like a channel that can support quantum effects. And that's a way to test whether gravity is quantum. This experiment can have two outcomes, as you said. So one outcome is that you set up the experiment, the masses are of the right range, the right energies and so on, and you do see entanglement. So you do see this effect, and you can say that it's only being created by gravity. This is a huge endeavor, but it's, I would say, within the 5-10 year timescale from now, experiments are close to the kind of level of sophistication that we need to do that. Now, if we see entanglement, then that tells us that classical theories of gravity are inadequate. They don't work. They are wrong. So specifically, Einstein's theory of relativity would have to be modified. It would be found to be incorrect in the sense that it's a classical theory and it's not adequate to describe this kind of situation. So you need these quantum theories of gravity. One of them, we don't know which one. Maybe we need an extra theory compared to the ones we already have. We don't know. But it has to be a quantum theory of gravity. And this opens doors to a very wild set of possibilities, really, because the theory of quantum gravity is a theory that would take this force that we know exists. It's a weak force. It's not very strong compared to the electromagnetic force. It's orders of magnitude weaker, but it's everywhere. Gravity, as you can see, anything that has a mass or energy gravitates. So everything really gravitates in the universe. And the fact that it has quantum features, the fact that this force behaves, in physics we think of it as a field or even as space-time, depending on how you think of it, but I'm talking about force just to make it simpler. The fact that this entity, the gravity, has quantum features means that we can incorporate it into a number of technological entities that currently we are not using it really. So one aspect is obvious, absolutely, is sensing. The kind of experiment that we have in mind, this one that can couple the masses to create entanglement gravitationally, requires a very high level of sensitivity to gravity as opposed to other forces. And so anything that is a sensor that relies on gravity or acceleration or stuff of that kind would be using this kind of technology that would be developed as a byproduct of the experiment would be automatically improved by inaccuracy by several orders of magnitude. So I think that the sensing set of possibilities would be enhanced greatly. So this is a very simple technological direct outcome of the experiment itself. If you want to go back to cities, I think sensing is a very ubiquitous thing. I think you can think of sensors being incorporated everywhere in a city to make life better. From trying to plan maybe underground things, so like you're thinking of checking whether there are underground irregularities, holes or things you want to know, the sensors are useful in that context. And they might be useful. Sudden accelerations, you can think of something like earthquake or sensors that could make things safer. I'm imagining some very wild scenario. I think sensors of acceleration are really useful in those cases too. So I think the quantum sensing opens up a number of very interesting possibilities. And of course, with vehicles and other things. But that's really just a very small thing that is almost an incremental thing. The broader picture is something that is really wild, as I said earlier, because gravity could be useful to, and we don't know this yet, but it could be that gravity has aspects that haven't been yet discovered simply because we don't have a theory of quantum gravity that can be tested. But it could be that there are ways in which you can use quantum effects in gravity to improve the efficiency of current engines. So this is a wild speculation, but because we don't know how to treat gravity as a quantum field yet, we know how to do it at low energies with approximations, but we don't know the right theory to do that. It's possible that this new theory will uncover effects that we don't know of yet. And I think one obvious thing that is interesting is whether the kind of force that gravity looks like, which is attractive at standard scales, might change its behavior in a very microscopic level due to this theory. So it could become non-attractive. There are wild speculations you can make at this stage. And all of these things could open up possibilities that this force could become useful in the context of an engine. It could be useful to imagine these kind of cycles that can regenerate themselves and reuse energy. So I think that the idea of using gravity as described by potential quantum theory of gravity to power an engine in a different way from what we've been thinking so far is something that this could open up. And then the third thing is that there could be a way to use gravity incorporated into quantum computing. So currently gravity isn't really used in quantum computing because, as I said, it's a very weak force compared to the electromagnetism, and tradition hasn't been thought of as useful. However, if you had the quantum theory of gravity, you could incorporate that into quantum technologies. And that, again, could lead to different effects that we don't know of yet. So these are the kind of directions I can think of just at the moment. But as usual with these discoveries, I think there are a lot of things you can't imagine simply because you don't know the theory yet. It's a bit like asking the founding fathers of quantum theory about the transistor. They didn't know that this would happen, but it did, and many other things. So somehow that's the level of discovery that we are thinking about. This experiment would really contribute to that, because currently some people are even thinking, oh, but you don't need quantum gravity. Gravity works just as well as it is. But this experiment say, oh, we do need it. And we need it to describe it at the low energy scales. So that would be a huge game changer. And now for the other result, if you didn't see entanglement, okay, one obvious thing is that you made some mistake, right? You didn't plug in some oscilloscope or something. The obvious thing that one thinks of first. It has happened in the past that people said, oh, energy is not conserved. And then turns out they didn't actually think that there was something that wasn't. I think it's a physics that really teach you not to get carried away when you violate something big, not to say, oh, something like energy conservation is wrong, because most likely there's something wrong in your experiment. But yeah, let's say you don't see the entanglement. Then that would be very interesting as well. It wouldn't mean necessarily that gravity is not quantum. So the fact that you don't see entanglement doesn't mean the gravity is classical. It means a number of possibilities. One possibility is that the current quantum theory of gravity that we are using at that level gives us the wrong predictions. So gravity could still be quantum, but we are using the wrong quantization method. This is a very important thing as well, because this theory of gravity that we're using is very well somehow corroborated by the fact that it has the right limit when you try to recover. So usually when you have a theory that's more general, you try to recover the ones you already know of. And so you try to recover what we call the Newtonian limit. So you try to make it look like taking some appropriate limits mathematically to look like Newton's laws in the right domain. And this theory that we have does have that feature. But it's an approximation, so it may not be the right way to take the limit. And if this experiment turned out not to provide the right answer, so there's no entanglement, it may mean that the theory that we're using is wrong. But the gravity is still quantum. So that would be a major blow immediately to all the quantum gravity theories that have been proposed so far. We would have to change them. But it may still be that we have to quantize gravity. It could mean that gravity is classical, in which case we have to question quantum theory. This, in my opinion, is the least likely, the least expected event. It is possible, and there are some eminent people who think that might be the case. You might have heard of Roger Penrose's theory of collapse. So Roger Penrose would bet on this, actually. And with him, other scientists, there's this tradition of thought that somehow, because they don't really like quantum theory, they would like it to fail in some way. And I think gravity is like the way to destroy quantum theory. It could be that's the case. It could also be that there is an extra force at play, which is not gravity, and is not electromagnetism, and is not the other forces that we know of, which is spoiling the effect, but we are not aware of that. That would be an even more interesting scenario where somehow the experiment picks up on a different force, which we are not aware of, that acts as noise and spoils the entanglement, the gravitational entanglement effect. This also would be a major discovery. So somehow it's a kind of win situation that whether you get the wrong result or a correct result, both directions would be very interesting. And the reason why this is that this experiment somehow taps into this regime where we're using quantum technology type effects, low energy therefore, but we're bringing in this new character, which is gravity, that hasn't been mixed with these things before. And so we are looking into a really direction that's different from the ones that have been looked at so far, which is why you can get these very surprising results, which are different from what you expect normally. And that's why somehow people got excited about this.
As you said, this is a 5-10 year endeavor, a really noble endeavor, and we are rooting for it to advance humanity's knowledge. to push the limits, what's possible, bring in new technologies, peek behind the curtain to find another curtain. My question is, how do you think about what kind of support structures are ideal to enable people to choose and pick up these types of endeavors? And I think you need to have a dense population who have extra resources to not just fight for survival, as we did when we were just hunter-gatherers, but have extra to rise above that need and push the limits of knowledge further and further out. What would a city look like, in your opinion, which enables the maximal amount of scientific advancement?
What would make the city the best environment for such knowledge to progress?
Okay, this is a very interesting question. And I think there are a number of aspects to be considered. So obviously, if we're talking about the issue of how to organize the structure of a city from a material point of view, we are thinking that some experiments of the kind I mentioned require these buildings that are well insulated. So obviously, you want noise to be at a minimum. And I think this can be done easily by putting these experiments in the basement, for example, and putting all sorts of insulating materials around. So you can have these kind of experiments really embedded into the urban structure, even maybe close to the city center, the way that it is here in Oxford or in Torino in the National Institute for Metrology, the INRIM labs, where we're thinking of doing these experiments. And this is kind of in sharp contrast with other kinds of experiment, like, for example, those to test particle physics or high-energy physics in general that require specifically built large-scale structures like accelerators and so on, which require much bigger spaces and are difficult to fit inside the historical city center of a European town. But now thinking more like broadly in terms of culture that an ideal city could foster in order for this experiment or this kind of science to be pursued, then there are all sorts of other things that come to mind. And specifically, it would be nicer to have a way to integrate the spaces where scientists, physicists specifically, do their work and the place where people live their everyday lives. So thinking we have museums where science is somehow made open access to attract sometimes even targeting, for example, young children, make them interested in cultural aspects of science and so on. But there are also schools and libraries, etc. But I'm thinking that the research institutes and the research institutions like universities and laboratories could be much better integrated in the urban environment to make them more open for people to visit and to see the output of the research going on in these places. And here, specifically theoretical physics is much harder to showcase than, say, biology or chemistry or medicine, where you can sort of show some concrete output of these fields, scientific research that impact directly people's lives. In the case of physics, these kind of impacts take longer to show. Sometimes they are much more unexpected. You can think of discoveries like the GPS, for example, that came out of the theory of relativity. This is something obviously that no one could envisage at the time when the theory was discovered. And yet several decades down the line, here we go with the GPS and many other technologies. So in that sense, I think it would be nice for the urban environment to, despite this difficulty of showcasing results from theoretical physics or physics more broadly, it would be nice to have an easier way to integrate these spaces where physicists do research with the spaces where people live their everyday lives and sort of make them more permeable in a way. We should really get creative and think of ways in which we can open universities and research laboratories, and maybe even having these different kinds of research environments, like a research institute that might be partly private and partly state-funded. All of these things that are things we have to experiment with could allow us to have more diversity in the way we even build research spaces and environments so that they become more open to people. And you can even actually invite people inside a laboratory and from time to time help them see how, for example, you can perform an interference experiment. You can actually hear or see the click of a photon entering a detector and so on. And all of these things are ways in which people can actually get closer to physics and enjoy it more than they currently do. And I think that's something that the urban environment could really help with.
Fortunately, 15, 20 years ago, in Hungary, there was a house called the House of Wonder, where they introduced the different inventions from Hungarian inventors. And that was fascinating with biology and physics and mathematics and everything else. Unfortunately, they ran out of money, so it doesn't exist anymore, but it was a good example. And I would love to ask you to give us an example to connect people to physics and your experiment. Could you give us a similar discovery in the scale of what will happen if you can prove that gravity has quantum effects? How would that outcome influence our life? What would be a similar change which happened previously?
This is a nice question because it allows us to explain how this experiment is really very similar in kind to the early experiments that happened between the end of the 19th century and the beginning of the 20th century. So we had this very interesting period where people started finding issues with the current theories. At the time, it was Maxwell's theory of light and waves and the classical physics, the way that I mentioned it earlier, so Newton's laws. And they noticed that they were inadequate to explain various experiments that started popping up with their evidence in those decades. For example, there was a very cool experiment, Rutherford and the structure of atom. So the fact that at some point we realized that not only did atoms exist, which was something that was contested for a while up until quite recently, but also they were structured in a way that the nucleus is made. The nucleus is made of protons and neutrons, and then the electrons are distributed more or less like a cloud around it. And so this overall neutral structure is achieved by mixing these charges, protons and electrons, not in a way that they are like in a pudding, which was one model that was at some point proposed, but they are really set up in this way. And the way this was discovered was by shooting various radiation onto a foil of metal by Rutherford. And I think this was a very important experiment because it allowed us to see a glimpse of what the actual structure of the atom was. Then further to that, I think there were extra steps which were very important. So the photoelectric effect, which was then explained by Einstein's theory, but I think it shows that light was absorbed not in a continuous way, but in quanta by metals and various solids. And I think this was a very important clue into understanding what quantum theory should be like. And then, the black body radiation experiment. So there were many of these experiments that at the time just made it possible to see a glimpse of why the current theories at the time were wrong and what kind of modification you could think of in order to make progress. Likewise, the experiment we are proposing now is an experiment that could allow us to show if we were to observe entanglement between the two masses, the way that I explained it earlier. So you have these two masses and you would like to create gravitational entanglement, which is a special kind of correlation that you can only create between quantum objects only through gravity. And if you can do that, you can observe the entanglement, then gravity must be quantum. Now, if you could observe this would be a huge step forward because it would say that classical theories of gravity are just wrong and they cannot describe this kind of experiment. So this would, on the one hand, corroborate theories like loop quantum gravity and string theory and linear quantum gravity. So all of the theories that quantize gravity and maintain locality would be supported by the experiment. And all of the classical theories of gravity, including Einstein's relativity, would be refuted. So this would be a huge momentous step because for more than a century since the proposal of quantum theories and general relativity, we haven't quite found a way of experimentally disproving either of them. And this would be a first falsification of one of these two theories. This would obviously open up huge theoretical avenues in the sense that it would bolster the quantum gravity programs. It would give them more evidence to try to provide more explanations that are tighter. And also it would provide a huge step forward in terms of the sensing technologies, the way that I mentioned earlier, because it would achieve a much better resolution for gravitational sensing than what we've done so far. And it would integrate gravity within a quantum computation effectively, which is something that hasn't been done up to this day. So this would be a huge change. And obviously the windows that quantum gravity may open onto the future are many, and the view from these windows is something that we can't really predict at present. It's something that's really hard to imagine at the moment, in the sense that the theory could actually give us insights into the thermodynamics of gravitational systems, and also into the way that they work at small scales, which is something that we haven't been able to test precisely so far. which is, we're open for finding some surprises there. And now for the other, this is a kind of win-win situation, because even if you find a negative result, and of course, yeah, I mean, you have to rule out immediately. There are cases where you find a negative result because the experiment hasn't been set up properly, and that's obviously not what we're thinking about. So suppose now the experiment has been set up properly, but you still don't see entanglement in the way that was predicted. Then this would also be a major problem that requires a non-trivial explanation. So one way to explain this would be that to say that quantum gravity as we know it is incorrect. So some of the ways in which we have been quantizing gravity may be wrong. And even though they're all designed to agree with Newtonian physics in a certain classical regime, there may be some different ways in which we can make gravity quantum, which are not the ones that we've tried so far, which may give a different prediction in this experiment. And the reason why we don't see entanglement could be simply that we haven't thought of the right way of describing gravity in a quantum way. So this would be a huge result in itself, because it would mean the current quantum gravity proposals aren't correct, and that even in the low energy regime, they are giving the wrong predictions. Now, of course, this may mean that gravity is still quantum, simply not described in the right way. It could also mean, even though that's not what I expect, but I think it could also mean that gravity is classical. However, not seeing entanglement doesn't mean necessarily that it's classical. As I said, it could be a number of other reasons why you don't see the predicted correlations. And then, for example, you could have the case where gravity is quantum, but you're not seeing the entanglement because there is an extra field or an extra force that is intervening, something that we haven't theoretically described yet, in addition to the current fundamental forces, which at that scale comes into play. This would be extremely weird and would require a lot of thinking to explain it, but there could be a possibility because we're really going to a domain that hasn't been tested yet. So we could have results of this kind. And then if gravity is classical after all, this means that quantum theory itself is wrong and is somehow non-universal and therefore requires modifications along the lines of what has been advocated, for example, by people like Roger Penrose and Dioschi and other theoreticians who've been advocating that, for example, you have to modify quantum theory to accommodate for something like a collapse of the wave function and so on. And this would be a major change itself in the way people think, because it would require quantum theory to be modified. And it would be a huge leap as well. So somehow both results are interesting and they would lead to really important developments, both on the theory side and the experimental side, and even technology. The thing I wanted to convey in this answer is really that the scale over which these changes should be expected is a huge scale. So they are not incremental experiments. There are lots of small experiments that people are conducting in this energy regime where you expect to see what has been predicted so far. You're improving the accuracy, and that's very important work as well. But what we are doing is really to go into a domain where we would be moving forward the current boundaries of knowledge much further than those experiments, because we'd be for the first time either confirming or disproving one of these two big theories that have been used so far to describe the universe and have been so far found correct. So I think this would be a momentous result. And that's why I'm really keen for this to be done, whether it's by the group that we are collaborating with in Torino or by a number of the other groups that are trying this out. I'm really hoping someone does this experiment because it would really open up so many possibilities and interesting avenues.
You mentioned how many smart people, I count yourself truly into that group, found new ways of finding an edge when, there's a contradiction there, we can push our knowledge forward here. So it's happened in the past, in the Middle Ages, and since then multiple times that, we are at the end of knowledge, we discovered everything, and then some person without or with a mustache discovers some nook, and then it expands into a whole universe. So on a high level, understand that knowledge is never ending. And this was Fanny's research with the smart city, that everybody wanted to build a smart city, which is a final thing. And then Fanny was like, the city is never finished. Can you give us an argument from like a physics knowledge creation point of view that why this knowledge creation is never ending? So we can tell people that a smart city never gonna get finished. It's only gonna get smarter.
This is something I haven't thought about explicitly so far. But I really like this idea of the extended phenotype. So the fact that life evolves and genes replicate and they're trying to replicate more and more. And I think to that end, they create an extra structure around them, which is something that they use in order to succeed in their replication. And the phenotype is whatever is harnessed by these genes in order to perform their self-replication. So, for example, the nest is part of the extended phenotype for the genes inside the bird and so on. And cities are part of the extended phenotype for the kind of knowledge that is produced by the human civilization. So you can see the way in which knowledge progresses is directly mirrored by the way in which towns and cities evolve in time. And I do think that these prophecies about the fact that knowledge has stopped evolving, which sometimes have been also echoed for cities, the cities have stopped evolving and so on, are prophecies that so far have been found out wrong, and they seem to be philosophically flawed for a number of reasons. In the case of knowledge, the way in which knowledge always progresses is, in fact, not necessarily progresses towards a better version of it, but let's say changes, is the fact that you find problems along the way. And these problems are like a small window that, if you start digging into it, will open up a huge portal to the next big thing. And in physics, it's been like this time and again. So there were people talking about two small clouds over the horizon about 1 century ago, just before quantum theory and general relativity were discovered. And they were saying that it would be impossible to think of how physics had it all explained and there was nothing else to discover. And then we found quantum theory and general relativity. And likewise, now we have the situation where these two theories have been so well confirmed in their respective domains, but somehow they don't go well together. And this in itself is a problem. And this problem is something that, if you dig into it, it will lead to a new theory, to a new explanation. So I think the problem is always a fertile start of something else. And so long as we find new problems, we'll always find some new knowledge to address them. Of course, we have to be on the lookout for problems. In the case of physics, it's very important, and in science in general, it's important someone is looking for these problems, even the hard ones, even those that, say, your supervisor tells you off when you're looking at them because they don't lead to certain predictable outcomes, and therefore they don't lead to grants or they don't lead to a steady job. Most of the times, I think you should still look at those problems, and if you find it fun, obviously, and I think pursue these problems despite all of these negative advice about it. So the fact that science still progresses and makes these changes through problem solving is something that cities benefit from a lot. And I think this has been clear over the history of human civilization. We started by gathering in bands, and I think this was reflected in the way we lived. And then the way in which then later on in, for example, the Renaissance, we had certain cities in Italy where you had knowledge growing very fast, and the urban landscape also evolved in similar ways. And then later on, if you think about the Industrial Revolution, for example, it fueled all sorts of changes in the way that cities are built. Stations showed up for trains, and then you had roads that had to be built so that cars could go on them. Regulations had to be put on so that people wouldn't run over other people, etc. And now it's clear that there are lots of things in science that could lead to urban changes, dramatic ones, I think. So I mentioned earlier, we haven't tapped into the possibility of using physics to imagine different kinds of vehicles. We are using mostly the flat structure of the cities to move around, sometimes underground. But what about the air, right? So I think you've had so many countless science fiction writings where people are imagining about flying cars and so on. We haven't managed to get there yet. But I'm imagining that this dimension, the orthogonal dimension to the flat landscape, is really yet to be explored, not just in terms of skyscrapers, but also in terms of roads, and roads in quotes, and ways in which you can connect people using different kinds of vehicles. And then, of course, there is the fact that we connected people differently now with the internet. But virtual reality, the advent of quantum computing with more powerful computers, could allow us to actually create spaces that are virtual where people can meet, even though they're really far apart. And so this may cut the need for physical travel, with all sorts of impacts also on the environment and so on, while still allowing the whole beauty of seeing people in person as if you were there. So these are things that might become possible. And I think this would also change the way in which cities are structured. They might spread them out even more and also change the way in which we build houses, condos, and urban aggregates. So all of these things are open. And I think there are many more things I can't imagine yet, which will be a direct product of knowledge evolving. And I think cities will expand on this knowledge and they will become even more interesting than they are now. And I think in both cases, really problems are key to expand knowledge and to make it somehow an open-ended quest for new problems and new knowledge and so on in terms of solutions to problems, etc.
Chiara, we want to be very respectful of your time, although we could ask you for hours and this would be very interesting. But as a almost closing question, what is your role in establishing the future of cities?
This is connected to what I said earlier. My main focus is really just doing research, and what I'm doing has the possibility of creating a very interesting new field of physics, both in terms of constructor theory, which is the theoretical work I'm doing overall, and specifically in regard to this experiment, which is one application of constructor theory to the problem of quantum gravity. I think these kind of studies, which are very abstract and theoretical, can have a huge impact on the way cities are built once they lead to an interesting outcome. And this is something that is often underappreciated, but I think it's really important to understand that sometimes, for example, as in the case of quantum computers, a discovery which happens as a result of something extremely theoretical and abstract, which is at the time was trying to understand computers and how they work and see whether if you use a different kind of dynamics to rule them, they could become different animals compared to the kind of computers that we use now. These kind of problems that seem very abstract and more like mathematical problems or computer science problems can actually have a direct impact on technologies. And this has been the case in this particular case that I mentioned. It's also been the case for Turing's work on Turing machines, computers. He wasn't going after the internet or trying to find a way to entertain us. He was trying to understand mathematics and how proofs work, etc. And in the end, he actually discovered something that has changed our societies dramatically and urban landscape as well. So one direction in which my work can shape the future of cities is really by producing new theoretical ideas that feed back into the technological loop and expand it. But also in my spare time, I like to write, and I not only to write, but also to think of ways in which you can explain some of these ideas of physics more easily to people that are not necessarily into this field, but they might be interested in hearing about it, or they find it fascinating, or even to children who don't know yet about this, and they might find it like an interesting field that they want to work in. And I think this is the way in which I can help, is to try to find ways, as I said earlier, where the urban landscape can help us be more open as a physics community towards the broader city-urban community. I would like to have more occasions where people can connect to us physicists and we can explain what we are doing in plain language so that people understand the beauty of what we're doing, really. And I think the spaces in which this can happen are spaces that still need to be developed appropriately within cities. We don't have them yet in place. And even thinking of building a new institute, which is something that I've been doing with some colleagues here in Oxford as well, an institute where you could have a different sort of research landscape compared to the standard university landscape or the laboratory landscape. An institute that, for example, could run in tandem with a museum, a science museum, which then allows us to give our ideas back into the sort of loop of knowledge within the town, within the city itself. All of these things are things I'd like to think about. And so in this way, my work has some byproducts also for the future of cities.
I so much agree with you, but we are really late with our questions. Do you have any closing comments or requests for the audience? How can people help you with your endeavors, this experiment and constructor theory and quantum theory?
I would say there are really just two ways that come to mind at the moment. So practically speaking, we are fundraising for these activities. And specifically, we are fundraising for the experiment to be performed in University of Turin in collaboration with the Theory Oxford team, which is led by me. This fundraising is something that's ongoing, and now is really the right time because, as I said, there's a kind of global race where other laboratories are trying to develop this kind of experiment. And the experiment could be developed on a number of different platforms, so it's important to sort of fuel the diversity of platforms over which you can implement this kind of work. So that's one concrete way in which people can help, which is just to support this fundraising effort that we are currently pushing. aside from the practical help in terms of funds, I think there is this broader help that I think people can give to physics in general and knowledge and science. And the fact that it's really important to get across this idea that activities like fundamental research in any field, particularly physics, but I would say any field, fundamental research that is undirected and doesn't have a specific purpose is essential, is vital for progress. It's something that's counterintuitive because when you see someone like a great scientist, I don't know, Schrödinger, who is trying to figure out how to write the equation for the new theory that will come after Newton's, you might think that's a very abstract endeavor and it sounds like it doesn't have any immediate impact on any of the particular technological challenges that one might have at hand. However, if you then consider what happened after that out of Schrödinger's equation and quantum theory more broadly came discoveries like the transistor and quantum computing and many other diagnostic devices that we're using, for example, for medicine purpose to do early detection of diseases, such as fMRI, etc. So all of these technologies really came out of this thinking abstractly within physics with no expectations and no immediate intention of producing a gadget within the next 3 years. These kind of ideas are essential. And if we forget about how important they are, we may end up just funding, just supporting ideas that have a predictable outcome. And this is very bad because it will mean that we won't be surprised anymore, because if you have a project that can lead to a predictable outcome, it means it's incremental. And then if you can predict the outcome, then that's not that interesting, is it? Because, you most likely will get that outcome if you put enough effort or money into it. But what's really interesting when you have a project that has outcomes that are not predictable to that degree, and that can lead to many, many unpredictable outcomes in the way that, say, discovering quantum theory did at the time. And this is something that people don't appreciate a lot, and it would be very helpful for people to remember this aspect and to remind other people about this. This fact that when you're looking for ideas of this kind, and you're a theoretician, for example, you're really there alone with your pencil and paper, and most of the ideas you have are to be thrown in the waste paper basket. So if you're tackling a challenging problem, maybe 9 out of 10 ideas won't work. Maybe more. Actually, the ratio could be even worse. But the one idea that works has this huge impact. It's really epoch-making, and it's something that changes paradigms. It shifts the way in which we live and has impacts well, well beyond whatever the person who thinks about that idea might envisage themselves. It's really important to be aware of this and to understand that, for example, therefore, when you're funding that person or that set of people that are thinking about these kind of ideas, you are budgeting into the funding also these 9 out of 10 ideas that you will have to throw away. But if you find the person who can produce top quality research and process throughout, you know that if you let them be, they will produce this golden idea that is like a moonshot type idea. And once that's produced, that has huge impact on all sorts of things. So this has to be remembered. It's important to spread this idea out, even among young people, young researchers, students as well. Remind them about the importance of being curious about just knowledge for the sake of itself. Because as soon as you have purpose for knowledge, you're clipping your mind's wings and you are no longer able to explore freely. Whereas if you're thinking, just following the fun and following what is it that interests you, you're just purely solving a problem. And that is the most likely scenario where great ideas will come out, even though they are hard to find. So I think this is really something that would be really helpful if people kept this in mind, and if it were more widespread knowledge, the knowledge about this process, how discovery works, how it's important to keep the flame alive. How do we do this? I don't know, but I think it's just so important that culture at all levels, from families to schools to universities, and even governments actually foster this kind of culture, because ultimately it's about the survival of our species.
Thank you so much, Chiara.
Thank you.
Thank you so much for having me on this podcast. It's been wonderful and I really enjoyed the conversation, and I hope it was fun for the audience as well.
And that's a wrap for this special episode as part of the podcast in 2025. It was really interesting to hear from Chiara about the need for the holistic approach. not to mention her description of the ever-evolving knowledge and thus cities. Richard Gere talked about how we can apply knowledge to the urban challenges, thus creating the new technologies in episode 274. You can find out more about Chiara online. All the links are in the show notes. As is the information on the charity to support Chiara's experiment, part of the Podcast in 2025 efforts. What was the most interesting part for you? What questions did arise regarding Chiara's approach to the future of cities? What have you learned from this interview? Let me know on Twitter at WTF4Cities or on the WTF4Cities.com website where the transcripts and show notes are available. You can also subscribe on the website not to miss any new episodes and leave some feedback. I hope this was an interesting interview for you as well, and thanks for tuning in.
What is the Future for Cities podcast?